Okay, so our key result has been this last boxed formula for the 2-point function. It's an exact result. All that we've used is Poincare invariance and unitarity. So this will hold in any quantum field theory. We also haven't said anything about the interactions. We could have had cubic interactions, quartic interactions, whatever you like. It could have been weak coupling. It could have been strong coupling. We haven't assumed perturbation theory. So this is a very general, exact result that we've obtained. So we're nearly ready to start discussing what does it mean. The only thing I want to do is come back and establish something about Z. So this wave function in normalization Z, we said that this was the probability with which a field will create a single particle state. And because of that, we had a prediction. We said that Z should lie between 0 and 1, as any good probability should. So now we would like to prove this. Okay. Now, when you want to prove a statement like this, again, we want an exact proof. So you need to start from an equation which is exact. So what equation do we start from? Well, it turns out that this is the correct equation to use. So remember when we quantized the theory, we said we always have to specify an equation which we will solve for whatever we're looking for. So we needed an equation for the momentum of the field pi and the field itself phi. And we postulated this equal time canonical commutation relation. Well, it turns out that this is the equation that's going to be useful for us to prove what values Z can take. Okay, so first observation is, so what is pi? Well, pi of t and x should be, or it's always the derivative of the Lagrangian with respect to pi dot of t and x. Then what does the Lagrangian look like? Well, we're dealing with a scalar field, so it's 1/2 d mu phi, d mu phi. Then we would have mass terms and interactions and everything else. And this, if you simplify it, is 1/2 phi dot squared. Well, if you differentiate a half phi dot squared with respect to phi dot, you're just left with phi dot of t comma x. So that, in fact, we have the commutator here of phi dot of t comma x with phi of t comma y. Good. Okay, so this is the equation that we want to use. Now, what is the thing that we know a lot about? Well, we know a lot about the Wightman functions. So we'd like to massage this into a form where it refers to the Wightman functions. So it makes sense then to calculate a vacuum expectation value. So let's do that. So the vacuum expectation value of phi dot of t comma x and phi of t comma y, that commutator, will be equal to the vacuum expectation value of minus I delta of x minus y. Good. Okay, so this is naught phi dot of t and x, phi of t and y, naught, minus, and now we've got the fields in the opposite order. Good. And then minus I delta of x minus y is just a number, so we can take it out, and we get minus I delta of x minus y. And here I'm using the fact that the vacuum is normalized to 1. Good. So this is the equation that we're going to use to prove what value z can take. And you can see it comes just from the canonical commutation relations. Now, this is not yet quite in a good form. So let's do the following. The first term we can write as a derivative with respect to tx of naught phi of tx comma x phi of t comma y, naught. And we can evaluate this at tx is equal to t plus epsilon. So the idea here is we're going to let epsilon go to 0, but we want tx to be just bigger than t. Why? Then tx is the latest time, and we know latest goes leftist. So time ordering would be consistent with the ordering of the fields that we've chosen here. And in the same way, let's rewrite the second term as d by dtx. Now we want the opposite ordering. So phi of t comma y, phi of tx comma x. And again, so that this is consistent with time ordering, we'll now take tx to be just less than t. So t minus epsilon. And again, we're interested in the limit that epsilon goes to 0. This should be minus I delta of x minus y. Good. So we're going to want to calculate these time derivatives. Now, let's look at the Weightman function. So where is all of the dependence on tx? Well, it's all sitting inside these functions, delta plus. Okay? So if you look at where's the tx dependence, well, it must be sitting there, it must be sitting there. So the thing that we have to know how to do is what is the time dependence of t plus. Delta plus, sorry. So we want to calculate the time derivative of delta plus, and just to remind you, this is what delta plus looks like. Good. Okay. So let's now evaluate what is d by dtx of delta plus x minus y. Yeah. Good. X minus y, and it could be mp squared or a squared. The answer that we get for this derivative will not depend on mp or a. And we're going to evaluate it at tx is equal to t plus epsilon. Well, this is equal to, it's d by dtx, and we should be acting on an integral d3p over 2 pi cubed to omega p, and then we have e to the minus I p naught, which is omega p, tx minus t plus I p dot x minus y. And we're going to evaluate this at tx equals t plus epsilon. Good. Okay, now if we differentiate with respect to tx, we will bring down a minus I, so let's put the minus I, and an omega p. Now the omega p over 2 omega p is just 1 over 2. Okay? And then what do we have left? Well, this is an integral d3p over 2 pi cubed. And then we've got, for the e to the I omega p tx minus t term, well, tx minus t is epsilon, and we're letting epsilon go to 0. So the first term of the exponential doesn't even contribute. And we've just got e to the I p dot x minus y. And that integral over p is something that I hope by now you really have memorized. It's just a delta of x minus y. So that this time derivative is just minus I over 2 delta of x minus y. And this is the formula that I wanted. Okay, good. Okay, so that is great. Let's just derive one more formula. It's a completely analogous computation. But let's do it, just to make sure that we've got everything understood. So for the next computation, I want to look at what is d by dtx delta plus and y minus x. Again, at mp squared or a squared, doesn't really matter. And tx is equal to t minus epsilon. That is what we're going to need for the second term in our equation in the green box. Okay, that's just the second term sitting there. What is this equal to? Well, let me write it down over here. And we can be pretty quick because it's not a difficult computation. So we've got an integral d3p 2 pi cubed 2 omega p e. Now we've got minus I omega p, and we have got t minus tx, and then plus I p dot y minus x. Good. Now, notice what's going to happen. So when we act with the d by dtx, we're again going to bring it down a factor, but this time it's not a factor of minus I omega p, it's a factor of plus I omega p. And then the computation is exactly the same, except for that one sign as what we just did. So this derivative lands up being equal to I over 2 delta of x minus y. Good. Okay, wonderful. So those are the two results that I wanted. And now, good. Now let's do the following. So I want to take establish exactly the same result, but for d by dtx of now the Weightman function, phi of x, phi of y, naught at tx is equal to t plus epsilon. So what is this equal to? Well, this will be d by dtx. And now let me plug in what this Weightman function is equal to. And we've got it over here. Good, over here. So it will be a z. Let's just write it. It will be a z delta plus x minus y, comma, mp squared plus an integral dA squared sigma of a squared z delta plus of x minus y, comma, a squared. Okay, and I have just used this formula over here for the Weightman function that we already established. Good. And again, we should be evaluating this at tx is equal to t plus epsilon. And now you see it's a really simple exercise. You just use the top blue box on this page. So every time that we differentiate a delta plus, we're just going to get a minus I over 2 delta x minus y. So we'll get a minus I over 2. Then we will have this coefficient of z, because that multiplies the delta plus, and then plus integral dA squared sigma of a squared z, that multiplies the other delta plus, and we'll have a delta of x minus y. And then it's equally easy to establish the following result. So naught phi of y, phi of x, naught at tx is equal to t minus epsilon. You see, we're going to have exactly the same formula, except everywhere we've got a delta plus of x minus y, it's going to be replaced by a delta plus of y minus x. And that means that the derivative with respect to tx, instead of giving us a minus I over 2 delta function, it'll give us a plus I over 2 delta function. So this we can write down immediately as just I over 2 z plus the integral dA squared sigma of a squared z delta of x minus y. So what's the equation that we wanted? It's this green boxed equation, okay? So it's the difference between the two Weightman functions must be equal to minus I don't know, how did that epsilon get in there? There's no epsilon there. Minus I delta of x minus y, okay? And what does this become? So let's take a look. So we want the result from the derivative of the first white plane function that's sitting at the top minus the second. Well, that's pretty easy. That is just minus I, because minus I over 2 minus I over 2 is just minus I. And then we've got Z, and then we've got 1 plus integral dA squared sigma of A squared times by Z. Sorry, we've taken the Z out. Good. Is equal to minus I, sorry. Oh, we still need the delta function, delta of x minus y. This must be equal to minus I delta of x minus y. The minus I matches on the two sides. The delta of x minus y matches on the two sides. So what we learn is z multiplied by 1 plus the integral dA squared times sigma of a squared must be equal to 1. And that tells us that z must be equal to 1 over 1 plus the integral dA squared sigma of a squared. This is an exact result, okay? Now let's see what it means. Now remember that sigma of a squared must be greater than or equal to 0. So let's see what we get for the values of the integral dA squared sigma of a squared, okay? Well, if sigma of a squared is actually equal to 0, then this integral will be 0, okay? But if it's not 0, this integral has to be bigger than 0. So this integral must be greater than or equal to 0. And, you know, if sigma of a squared is big enough, a squared we're integrating from 0 all the way up to infinity. So it may happen that this integral diverges. So all that we can say with confidence is that this integral lies between 0 and infinity. When this integral has the value of 0, then z is equal to 1. And when this integral has the value of infinity, then z would be equal to 0. And if the integral is in between, then z has a value in between 0 and 1. So we have just managed to prove that z does take values between 0 and 1 as an exact statement about quantum field theory, using only Poincare invariance and translational invariance. And this is perfectly consistent with our interpretation of Z as the probability with which our field creates a single particle state. So that's the interpretation of the wave function renormalization. Okay, great. So now we really are getting a lot of insights into this equation in the black box. We'll continue in a moment.